Welcome. This is Professor Nathan Weezy from Marquette University. This section we're going to talk about single-phase PLL using single precision floating point for the digital control of power electronics. So we've already gone over two other lectures. One is just the continuous time variant of this, and then the fixed point. This one will be the floating point. And I'm going to start with kind of a word of caution with the floating point. I would strongly suggest, if you're using this a real application in industry, that you make sure that you are using a microprocessor that has a floating point unit. And the reason is quite simple. It's not that you can't do this with a processor that doesn't have a floating point unit, but a processor that has a floating point unit, instructions such as addition, multiplication, etc., can be done in 1 to 2 clock cycles relative to the frequency of the processor. Now, if you're using a processor that doesn't have a floating point unit and you're using floating point numbers in your C code, unbeknownst to the writer most of the time, when you go to compile, what the compiler is actually going to do is realize, hey, you don't have a floating point unit on this processor, and load a library to do these calculations. And the net result is that, for instance, a simple addition may require 10, 15, 20, 30 instructions just to do one addition. And if you think about it, that adds up pretty quickly because all these filters are a lot of addition and multiplication. And that's just for one filter. If you have multiple, this adds up very, very quickly. The same goes for multiplication, addition, sign, any function that you do on a single precision floating point number. If you don't have a floating point unit, will incur a large penalty. Especially, and the other thing too is if you're making a lot of library calls, unbeknownst to the writer, because you need to jump to make these calls, you're going to incur overhead to jump to these libraries to actually do that. So that adds even more instructions. You got to save the stack, restore the stack, jump, the cache line, the delay line in the cache, the processor needs to get filled up. So you incur a lot of loss of speed and efficiency. So when you're using floating point, make sure you have a floating point unit on your processor in order to reap the benefits. Okay, we're going to pick up where we left off on the other two designs. We're going to use the same low-pass controller, except for being in the digital domain. Same gain here, same low-pass filter structure. Our voltage-controlled oscillator will simply just be a integrator in the discrete variant. What I've included again is some MATLAB code we can go over quickly in order to talk about what I'm actually doing here. So a lot of this is the same, so I'm not going to go over most of it. It's in the other lecture, but this is the gain of the VCO, which is scriptable on line 14. You have the bandwidth, and you have the damping selectable in the script, so you can do whatever you want in terms of selecting that. Equations 18 through 21 will essentially set up for you to solve for the gain K1. So this is the gain of the low-pass filter. And omega F, this is going to be the pole of the low-pass filter. Line 27 just constructs a transfer function object within MATLAB using those two gains, K1 and omega F. And then line 29, we're setting the sampling frequency for our digital controller. 30, we create a Z transform object, Z, with that same sample time. S back is our backwards Euler approximation for S. And what we do is we plug that into 32 and replace that in for our low-pass filter, and GC dig backwards, or line 32, will be our controller digitally for this low-pass filter. And we do that for zero-order Holden, Tustin in 33 and 34 via the C2D function, which is a built-in MATLAB function for converting from continuous time to discrete time. Okay, now some of the new stuff we have here is line 36 through 52. We're going to convert at least the backwards Euler and the Tustin digital controller to a floating point number representation and have the C code generated for us for those, defining those single precision floating point numbers. What I want to point out here is that GC dig backwards is an object, right? It's a transfer function object. If you hit period numerator and the first cell, that is a vector of all your coefficients of the numerator, and that is the same for the denominator. We can call the denominator object there, and the first cell will have all the coefficients. And then we wrap it with this. This is a command single. What single does is it'll take an input of a single number or a vector of numbers and convert them to single precision floating point numbers, which is exactly what we want for a controller. So essentially this is going to spit out a vector, B coefficient and A coefficient, a vector of single precision floating point numbers that represent the gains that we'd like to have for a digital filter. Now I do the same here in this code down below for Tustin. The only difference here is that I'm passing in Tustin transfer function object instead of the backwards Euler, and I get these coefficients. Now these two lines down here are the output of my two controllers in floating point precision numbers. Generally what I do is when I'm done and I have a good design, I will copy and paste this into my C code, and those are the coefficients for my two different controllers. Depends on which one I want to use, but those are the coefficients in single precision floating point format. We can now take a look to see what the controllers look like. They're going to look very similar. This is the backward Euler low pass filter. Again, you can see a couple cycles right away. We need to speed up, and then pretty much we're locked on. This is like slow down, speed up, slow down. So we're teeter-tottering between two phases, and you can see right away the phase speeds up here, speeds up a little more, and then we're essentially locked from here on out. Okay, this is very similar to Q21. We're just using a different number system to represent it. Our control effort and PFD and phase are now in floating point, which looks familiar. We have 2 pi, which is 6.28 as the peak for our phase. So that looks very familiar to us. Now if we do the Tustin transformation for the low pass, this is what a transfer function looks like. I have the gains in the previous stuff. I ran it again here, a simulation, and essentially we're getting the same thing as we got before. We'll speed up in 2 cycles, and then pretty much after here we are locked. Okay. All right, so now let's check. We're going to go do this again for the PI controller. All this code from line 1 to 16, all this is doing is producing the controller in the digital domain for the low pass filter. These first few lines are giving us our gain and phase for our, they're giving the KP gain and the KI gain for our PI controller. And then down here, essentially what we're doing is converting these to the digital domain using the same code that I've done previously. Here we're going to go ahead and output the numbers for our transfer function in the digital domain as single precision floating points. For C codes, we can copy and paste. That's what these two do. One for backwards, one for Tustin. Other than that, the code's the same. These coefficients are much different than the low pass because this is implementing or attempting to approximate a PI or a proportional integrator. You can see the difference between forward or backwards Euler and the Tustin is very small. So the A coefficients are exactly the same. And if we look at our B coefficients, yeah, they're very, very close. So I don't think you're going to note any difference between these two in this case because of how close they are. So if we look at this, there's our controller for the backwards Euler, and we're using backwards Eulers with floating point numbers. You can see right away we have to speed up. Remember, this one's not damped well, so we overshoot, and we got to slow down, slow down, slow down. And then somewhere over here, we're in the lock state. This is very similar to what we've seen before. And we'll check lastly our other controller. This is for the Tustin approximation for our controller, and again, we're using floating point numbers. The result is almost exactly the same. So these are some controllers that work. For this type of implementation, I would just stick with the low pass. You don't need the integrator in this case because you have an integrator in your VCO. But it was a useful thing to do here just to see, what type of control structures do you need for certain types of plants. In this case, there's not really anything to use a PI controller for, and it's really actually hard to damp it because you're adding an additional minus 90 degrees on top of the integrator that you already have in your system. So thank you for your time. This concludes the discussion on the floating point version of the single phase PLL. Thank you.